Welcome to another deep dive. Today we're unpacking a challenge that vexes many cloud architects and DevOps engineers. How do you build a multi-region database setup using DynamoDB without, well, breaking the bank?
Exactly.
Our mission in this deep dive is to give you a genuine shortcut to mastering this concept, especially for those high-stakes moments like a technical interview. We'll show you how to potentially slash cost by a staggering 70% for what might seem like an inherently expensive global database. This deep dive is really custom tailored for you, pulling direct, actionable insights from our source material, transforming potentially overwhelming info into, clear, memorable takeaways.
That's right. And what we're really digging into today is a core tension in cloud architecture. It's that balance, right? How do you get global availability, making sure your application is fast and resilient for users everywhere, but also handle the often overlooked economic realities of data transfer? DynamoDB Global Tables offer incredible convenience, almost too much convenience, because that out-of-the-box simplicity can sometimes hide a pretty unsustainable cost structure if you're not paying close attention. It's actually one of those gotcha questions in a lot of interviews.
Right, the hidden costs.
Precisely. So let's just jump straight into the problem statement we're dissecting today. This is the kind of question you might get. How do you architect a cost-optimized multi-region active DynamoDB setup to reduce data transfer costs, potentially by 70%?
Okay, that's a meaty question.
It is. And the immediate high-level answer, the one you'd want to give in the first 30 seconds or so, it's basically this. While standard global tables provide seamless replication, they can lead to surprisingly high costs. Mostly due to replicated write capacity units, which, remember, are charged at 1.5 times the normal rate, and also significant cross-region data transfer fees, typically around, say, 0.9 to 0 or into 12 cents per gigabyte. But the crucial part, the part you absolutely need to add, is that by applying smart architectural patterns like a hub-and-spoke model, you can dramatically cut these expenses.
Okay, that 1.5x rate and those transfer fees definitely sound like immediate red flags. But I mean, global tables are supposed to be this magical, fully managed solution for global scale, aren't they?
They are marketed that way, yeah.
So what are the primary cost drivers then? What makes standard global tables so expensive in the first place? What's the hidden trap here that catches so many people out?
That's precisely it. It's easy to fall into. When we break down the cost analysis, a few key factors really jump out. First, like I mentioned, there are the replicated write capacity units, or WCUs.
Right.
Think of these as the currency DynamoDB charges you for every write operation. It's essentially the computational effort to process your data. Now, here's the kicker. Every single write you perform to a global table triggers replication to all the other regions where that table exists.
All of them.
All of them. This effectively multiplies your write costs by the number of regions you have. And on top of that, those replicated units get charged at that 1.5x premium. So if you write once in one region...
You're paying for that write plus 1.5 times for each copy in every other region.
Exactly. It's not just the initial write, it's every copy, and at a higher rate, almost like a global processing fee, as you put it.
Okay.
And second, and this is often the biggest hidden culprit, is cross-region data transfer. This is a straight per gigabyte charge for any data moving between AWS regions, like I said, usually $0.9 to $1.12 per GB. When you have that full automatic replication turned on, every single byte you write in one region that needs copying elsewhere, it incurs this fee.
So every write generates transfer costs to multiple places.
Correct. Third, you've got straightforward storage multiplication. Your data is stored in each region you replicate to, by definition. So you're paying separate storage costs for each identical copy.
Makes sense.
And finally, there's a smaller but still present request routing overhead. Just coordinating across multiple regions naturally adds a tiny bit of latency and processing costs to manage that global consistency. It's not huge, but it's there. To put this into a really relatable analogy, maybe think of your multi-region DynamoDB setup like a global retail chain with warehouses in different countries, right?
Okay, I like analogies.
The traditional approach, the standard global tables way, it's like insisting on keeping identical inventory in every single warehouse. And the moment a new product arrives at one warehouse, you immediately ship copies to all the other locations worldwide.
That sounds expensive and probably unnecessary most of the time.
Exactly. Incredibly expensive and often totally unnecessary. So it's like we've been running this global retail empire with a very enthusiastic but maybe fiscally irresponsible shipping department.
Yeah, shipping everything everywhere, all the time.
Precisely. And that's the cost problem in a nutshell. Standard global tables means every time you add inventory that's your right data to one warehouse, you automatically ship copies to all the others. Each one of those shipments costs money. Those are your data transfer fees. And each requires local staff to receive and process it. Those are your replicated write capacity units. And remember, those staff members handling the incoming shipments, they're getting paid 1.5 times their normal wages for this cross-border work.
Ouch.
Yeah. So let's use a concrete example. Say you have 4 regions in your global table setup, and you write 1 gigabyte of data in a month. You're paying for that original 1 gigabyte write capacity. Plus, you're paying for 3 gigabytes of cross-region data transfers, each at maybe $0.10. And you're paying for 4 times the write capacity units, the one original, plus 3 replicated units at the 1.5x rate.
It adds up incredibly fast.
Extremely fast. And this is where, frankly, a lot of companies get blindsided. They just clicked enable global tables in the console, assumed AWS Magic would handle everything efficiently, and then didn't really check the bill closely until it was too late.
Okay, that makes the problem crystal clear.
Yeah.
Now, the goal you mentioned is achieving a 70% cost reduction. That sounds almost like, well, like magic itself when you're talking global databases.
It seems dramatic, I know.
So how does this optimization architecture actually work? What are the core concepts that allow for such a drastic cut? This is where it gets really interesting for anyone listening.
It really is. The core of the optimization architecture lies in fundamentally shifting from that replicate everything everywhere immediately model to something much more intelligent and targeted. First, we look at regional write specialization. Instead of allowing writes to happen in any region, which is the default global table behavior, we designate specific regions, often just one primary region, for handling all, or at least most, of the write-heavy operations.
Okay, so funnel the writes to one place.
Pretty much. We still maintain read replicas globally, though. That's key. Users can still read data with low latency from their nearest region, but the writes are centralized. Second, and this is a huge one for cost savings, is implementing intelligent data compression. You actually compress the data at the application level before it even needs to cross region boundaries.
Ah, so you shrink it first.
Exactly. Our sources showed this can reduce the actual transfer volume by up to 80%. That directly translates to massive savings on those per gigabyte data transfer fees.
80% is huge.
It's a game changer for the transfer costs. Third, we employ conditional replication patterns. Instead of just blindly replicating everything, we leverage DynamoDB streams.
Okay, what are those again?
DynamoDB streams are essentially a time-ordered sequence of item-level changes in your table, our real-time log. You can hook these streams up to AWS Lambda functions. These Lambda functions can then inspect the changes and decide selectively whether or not to synchronize that specific piece of data to other regions based on business logic. So data is only replicated if it actually needs to be, not just automatically.
So you're filtering the replication straight.
Precisely. Maybe only replicate user data to the region they're active in, for example. And finally, a technical but important point, VPC endpoint optimization. By routing all your internal AWS service communication, including DynamoDB traffic between your application and the database through VPC endpoints.
To keep it off the public internet.
Exactly. You keep that traffic within the secure, private AWS network. This often eliminates the more expensive internet data transfer charges you might otherwise incur.
Okay, so we're not just throwing data around globally anymore. We're compressing it, picking and choosing what gets replicated, and keeping the traffic internal to AWS as much as possible. That sounds incredibly clever on paper.
It is a shift in thinking.
But when you're actually sitting down to build this, maybe prepping for that interview question, what's the first tangible step? What does the implementation strategy look like when we're actually putting these brilliant pieces together?
Right, the practical implementation. The overarching strategy we generally recommend is what's called a hub-and-spoke architecture.
Hub and spoke. Okay.
This means you designate a primary write region, the hub. This region handles all, or the vast majority, of your write operations, and you'd ideally choose your most cost-effective region for this hub. For many folks, that tends to be US East and Virginia, as it often has some of the lowest AWS service costs.
So pick the cheapest region for the heavy lifting.
Exactly. Then you have your read replicas, the spokes, in your various edge regions closer to your users. These replicas are eventually consistent, meaning data written to the hub might take a moment, maybe seconds, to propagate out to the spokes.
Eventually consistent, right?
Yeah.
Trade-off there.
It is a trade-off, yes. But these spokes provide that crucial low-latency local read access for users in those regions. Now, to manage the actual data flow from hub to spoke, you often implement batch synchronization. Instead of real-time replication for everything, you might use scheduled Lambda functions, perhaps triggered by CloudWatch events, to replicate less critical data during off-peak hours. This can sometimes be cheaper or reduce contention.
Matching it up.
Yeah. And crucially, as we discussed, you use conditional updates via those stream-triggered lambdas. You only replicate data that meets specific business criteria. For instance, if a user profile update happens in the hub, the lambda might check if that user is active in, say, Europe. If yes, replicate it to the European spoke. If not, maybe don't bother sending it there.
Smart filtering again.
Exactly. And finally, don't forget about capacity management. For workloads with predictable patterns, you can get significant savings, sometimes up to 30%, by switching from on-demand capacity to reserved capacity optimization.
Buying ahead for predictable load.
Right. And for variable traffic, you absolutely should use DynamoDB's auto-scaling features to ensure you're always right-sized, scaling up and down automatically while maintaining cost predictability. Maybe let's revisit our retail analogy to really cement this 70% cost reduction strategy.
Yeah, let's do that.
Okay, so instead of identical warehouses everywhere, think of it now as the regional specialization approach. You have one primary warehouse that's your hub, your designated right region. This warehouse handles all the new inventory additions, and critically, it's located in the cheapest possible spot.
Got it. Central cheap hub.
Then you have local showrooms. These are your read replicas, the spokes. They display the products nicely for local customers, ensuring that fast browsing experience, low read latency, but they don't try to maintain a full, identical inventory of every single item from the main warehouse.
Okay, just what the local customers need to see.
Exactly. And finally, you implement smart restocking. This is your selective replication logic. You only ship the popular items or items relevant to that specific region's customers from the primary warehouse to the local showrooms. You base this on demand signals or user activity.
Not just shipping blindly.
Right. And to make it even more efficient, you use bulk shipping whenever possible. That's like our batch transfers, maybe moving inventory during off-peak hours using cheaper shipping rates, just like those scheduled Lambda functions we talked about, moving data when network traffic might be lower.
That retail analogy really helps visualize the difference between the two approaches. Okay, the theory sounds solid, the analogy works. But the numbers, you mentioned a 70% reduction. That's huge.
It is.
Can you walk us through a practical cost calculation? Show us how these numbers might actually add up in a real-world-ish scenario to demonstrate how that 70% reduction is achievable. Give us the proof, basically.
Absolutely. Let's crunch some hypothetical but realistic numbers. Imagine a scenario where you're writing about 100 gigabytes of data monthly. Before optimization, let's say you're using a standard 4-region global table setup.
Okay, 4 regions, 100 gigabyte, that's right.
Your write capacity costs. Well, you have 100 gigabyte times 4 regions. Let's use a ballpark figure of $1.25 per WCU month equivalent for simplicity. So 100 by 4 by $1.25. That's around $500 just for the write capacity, remembering that includes the 1.5x premium on the replicated writes.
$500 for writes? Okay.
Now, data transfer. Your 100 gigabyte original write needs to be replicated to the other 3 regions. So that's 300 gigabytes of cross-region transfers. Let's use $0.10 per giga as an average cost. 300 gigabytes times $0.10 is $30.
Right.
So your total monthly cost before optimization is roughly $500 plus $30, $530 plus storage, but let's focus on writes and transfer as they dominate.
$500 a month. Got it.
Now let's look at the after optimization scenario using our hub and spoke model with compression and selective replication.
Okay, same 100 gigabyte writes.
Your write capacity cost drops dramatically because all writes now go to a single primary region, the hub. So it's just 100 gigabyte times 1 region times 125. That comes down to only $125.
Wow, okay, big drop already.
Huge drop. Now, data transfers. Let's assume we achieve that 80% compression we talked about on the data before it's transferred. So instead of sending the full 300 gigabyte to the replicas, we're only effectively transferring 20% of that, which is 60 gigabyte.
Okay, 60 gigabyte compressed.
60 gigabyte times our 710 cents per GB rate. That's now just $6 for data transfer.
$6, down from 30.
Exactly. Then we need to factor in a nominal cost for running the read replicas themselves. Let's maybe estimate $25 a month for that. It depends on read volume, of course.
Sure, got to account for the spokes.
So add it up. $125 for writes, plus $6 for transfer, plus $25 for replicas. That brings your total monthly cost down to approximately $156.
$156 compared to $530.
Precisely. That's a reduction from $530 down to $156. That clearly demonstrates the roughly 70% cost reduction we were aiming for. The numbers really bear it out.
That's
right?
Yeah,
Because
that's a massive difference when you see the numbers laid out like that. It truly underlines the value of, thoughtful architecture
right.
over just clicking defaults.
Absolutely.
But, okay, with such significant architectural changes, moving from the easy, fully managed global tables to this custom hub-and-spoke thing, what's the catch? There must be trade-offs, right?
Yeah.
What are the things people need to consider? It sounds like a lot more work for the engineer.
It absolutely is more work for the engineer, and that's honestly the primary trade-off.
Yeah.
You're trading AWS-managed simplicity for cost savings and control, which requires effort. Let's compare the key architectural considerations side by side. For write pattern, standard global tables let you write in every region, which offers ultimate flexibility, sometimes called multi-master writes. Our optimized approach, however, centralizes writes to a single primary region. This simplifies achieving write consistency, but introduces a potential single point failure for writes if that primary region goes down. You need to architect for that failover scenario.
Okay, flexibility versus single point of write origin.
Exactly. For data transfer, global tables do full, immediate replication of everything to all regions. Our optimized model uses selective and compressed transfers. It's much cheaper, but requires more upfront thought and ongoing maintenance about what data truly needs to be replicated where and how quickly.
More logic involved.
Definitely. Regarding consistency, standard global tables offer eventual consistency across all regions for all data. Our hub-and-spoke setup typically gives you strong consistency for writes within your primary region, since all writes go there, but the read replicas in the other regions will remain eventually consistent. The lag depends on your replication mechanism.
So strong in the hub, eventual in the spokes. Got it.
Then the cost structure, which is perhaps the most compelling difference. Standard global tables tend to scale cost linearly. With the number of regions you add a region, multiply the cost factors. Our optimized approach aims for a more logarithmic scaling, where adding more read regions, spokes, doesn't proportionally explode your core write and transfer costs originating from the hub.
Better scaling curve.
Hopefully, yes. And finally, complexity. This is the big one. Standard global tables are largely AWS-managed simplicity. You enable it, configure a few things, and it, mostly works. The optimized hub and spoke requires significant custom orchestration. You're building the replication logic yourself with Lambda functions, managing the routing, monitoring the compression. This is where the real engineering effort comes in.
Right, you own the replication pipeline.
You do. And just to give you a conceptual idea of what that custom orchestration might look like without getting into code, take the DynamoDB streams with Lambda for selective replication. You'd have a Lambda function configured to be triggered by those change events from your primary DynamoDB table stream. Inside that Lambda's code, you'd write logic to filter the incoming records. For example, it might check a field on the updated item, say, user last active region. If that region matches the target spoke region the Lambda is responsible for, then it proceeds to replicate the data.
Okay, filtering logic in the Lambda.
Right. And maybe before sending that data on to the spoke region's DynamoDB table, the Lambda would also apply a compression algorithm like gzip to the data payload to reduce its size. Then it makes the POO item or update item call to the replica table. Then for the regional routing logic, this typically lives in your application layer, maybe your API gateway, your load balancer, or the application code itself. It needs to be intelligent enough to direct requests. Any operation that modifies data, a post, PUT, delete, would always be routed to the endpoint associated with your designated primary region, say DynamoDB.us east-1.amazonos.com.
Writes always go to the hub.
Always. But read operations, GET requests, could be routed to the user's local replica region's endpoint, like dynamodb.eu-west-1.amazonos.com for the lowest possible latency. It requires that application-level awareness of where the user is or where the data should be read from.
So the app needs to know about the hub and spokes.
Correct. It requires that extra layer of intelligence in your application, but that's how you gain that granular control, optimize the traffic flow, and ultimately achieve those significant cost savings.
Okay, that makes sense. It's definitely more involved. So let's say you've gone through all that effort, you've built this lean, mean, cost-effective setup. How do you make sure it stays optimized? How do you ensure it performs well over time? What kind of troubleshooting framework or monitoring should you have in place to catch issues before they become big problems, or maybe prevent those costs from slowly creeping back up?
That's a crucial point. Maintaining an optimized multi-region setup is absolutely an ongoing process. It's definitely not a set-it-and-forget-it kind of deal. First, for cost monitoring, you absolutely need to be using tools like AWS Cost Explorer. Specifically, filter it to track your data transfer charges, breaking them down by the source and destination region pair. This lets you pinpoint exactly where your data is flowing and immediately spot if unexpected expensive transfers are happening.
Watching the transfer costs like a hawk.
Exactly. You should also set up CloudWatch alarms based on metrics like inter-region data transfer. Have alarms trigger if cross-region traffic spikes unexpectedly beyond your baseline, and critically, implement application-level metrics. Track your actual compression ratios. Are you still getting that 80% reduction? Log metrics about your replication decisions. How often is data being filtered out versus replicated? This is where I think many engineering teams sometimes miss the ball. They build the optimization, but don't continuously validate that it's still saving money effectively.
Measure the savings, not just assume them.
Precisely. Second, for performance validation, you must continuously monitor the read latency from your edge regions, your spokes. These are what your users are interacting with for reads, so you need to ensure their experience remains acceptable, meeting your SLAs. You also need to track the replication lag between your primary hub and your replica spokes. Tools like CloudWatch can help here too, maybe by tracking timestamps on items. This helps you understand the trade-off you're making between cost savings from maybe batching or selective replication and the data freshness requirements for your application. Is a 10-second lag okay? Is 2 minutes? You need to know.
Balancing cost and freshness.
Exactly. And importantly, you need to regularly test your failover scenarios. What happens if your primary write region actually experiences an outage? Does your application correctly redirect writes to a designated backup region or handle the failure gracefully? You have to test this periodically.
Don't wait for a real outage to find out.
Please don't. Finally, for capacity optimization, even within this optimized hub-and-spoke model, your workloads will likely fluctuate. So make sure you're utilizing DynamoDB auto-scaling effectively for both the hub and the spokes to dynamically adjust read and write capacity as traffic changes. Keep monitoring your utilization patterns, especially if you've purchased reserved capacity. You need to right-size those commitments to ensure you're not consistently paying for idle capacity you don't need.
Right-sizing is key.
Always. And one more advanced technique. For very frequently accessed data, consider implementing a read-through caching layer in your spoke regions using a service like Elasticache, Redis, or Memcached. This can absorb a lot of the read load, further reducing the number of reads hitting your DynamoDB read replicas, which can cut down your DynamoDB costs even more.
Caching for the hot data makes sense.
So let's try and summarize the critical points here for you to carry forward, whether you're, actually building out a new architecture or perhaps discussing this very topic in an interview setting. Firstly, achieving global availability for your applications doesn't have to mean deploying uniform, expensive, replicate everything everywhere infrastructure across every region. There are smarter, more cost-effective ways.
Think beyond the default.
Exactly. Secondly, cross-region data transfer is very often the hidden major cost driver in these multi-region setups. Techniques like intelligent data compression and implementing selective data synchronization are incredibly powerful tools to combat this specific cost.
Focus on the data transfer costs.
Definitely. Thirdly, architecting using a hub-and-spoke model, typically with a single primary write region, can dramatically reduce your overall costs compared to just relying on a standard, fully replicated DynamoDB Global Table. Fourth, while it undoubtedly introduces more complexity and requires more engineering effort to build and maintain, this kind of custom orchestration of your data flow offers you significant control over costs and efficiency gains.
Complexity is the trade-off for control and cost.
That's the core trade-off, yes. And finally, continuous, vigilant monitoring of your costs, your application performance, especially read latency and replication lag, and your capacity utilization is absolutely essential for maintaining an optimized multi-region setup over the long term. Don't just build it, keep watching it. That's all for this topic. Stay tuned for the next DevOps Cloud interview question.
Wow, what an enlightening deep dive. That really clarifies how standard global tables can sneakily inflate costs, and how a more deliberate architecture like hub and spoke can make such a huge difference. It truly makes you think about how we can be so much more deliberate with our cloud architectures, finding those sweet spots between high performance and genuine cost savings.
It's all about understanding the levers you can pull.
Absolutely. So as you, our listener, think about designing your own cloud architectures, here's something to mull over. Where else might a hub and spoke or a selective replication pattern be applied? Maybe beyond just databases. Where else could you optimize for both performance and cost using similar principles? Something to think about until our next deep dive.